Wednesday meetup. We will be starting momentarily, and it gives me great pleasure to introduce to you some speakers around DevOps and CloudOps. We had a slight change in the agenda. One of the speakers from CFPB was unable to make it. We were not able to get their clearances to be able to speak externally in time. So my apologies for the folks that were looking to speak or to hear from the Consumer Financial Protection Bureau. But we have an awesome speaker, Danny, from the Netflix platform engineering team, and he was very kind enough to provide us a little bit more content than we would have had before. So again, welcome. Thank you for this first inaugural webinar format that we're doing for the Cloud DC Meetup. Just a quick thing about the Cloud DC Meetup. You can go to www.meetup.com/clouddc. You should be able to see the URL on your screens. We are a group of technology enthusiasts that look at different kinds of cloud solutions and how they can help organizations do a better job at sort of modernizing their applications and their infrastructure. And we have normally done in-person events, and we thought perhaps we would appeal to a broader audience if we tried this webinar format. So do let us know your feedback, and if you like this, we will definitely continue this. With that sort of introduction, really quickly, I want to get out of your way and present to you Danny, who will give you an overview of some of the operations and interesting things that Netflix has been doing in the space of cloud operations. And I also want to give a quick plug for the Netflix team. They've just been phenomenal innovators in the cloud space, and they're always looking to hire good people. So if you're interested in cloud technologies and you're interested in operations and platform engineering, please do visit the Netflix careers page. And also Danny has promised to be responsive and respond to any emails if you have questions around Netflix career opportunities in the cloud operations and development space. With that, I want to get out of your way and introduce to you Danny from the Netflix platform engineering team to walk you through some interesting solutions they have built. And you should feel free to go in and ask questions using the GoToMeeting software. And I will try and make sure that I read out those questions and present them to Danny. Danny, good morning to you, and thank you very much for being part of the Meetup webinar. I will make you the presenter now.
Thank you. Thanks, Gaurav, and thanks for the introduction. Hi, everyone. It's really great that you're here. And I'll put up my slides first. Okay. So can you see the slides?
Danny, I can go ahead and see the slides.
Okay. Oops. Okay. Hi, everyone. Thanks for coming. Okay, so my name is Danny. I'm an engineer in the platform engineering team, so I work on different projects, but in the recent couple of years, I've mainly worked on the data pipeline side and also the real-time analytics integrated with the data pipeline. So without further ado, I'll just start the presentation. Somehow, just one second, let me minimize this meeting software. Okay, so a brief introduction of what Netflix is. Well, Netflix is a video streaming company, but really we generate a lot of logs. That's why sometimes we jokingly say Netflix is a log generating company that also happens to stream movies. But why do we generate so much data? Well, to us, the data is the most important assets at Netflix. Right. The reason is so data is the most important assets in Netflix because we do another analysis with the data. We use data to predict what's going to happen. We use data to find out usage patterns. We use data to monitor and operate our services. And if all the data is easily available to all the teams, then it can be leveraged in new and exciting ways as well. That's our belief. So with that, we started building our data pipelines. But before we go on to the details of the data pipeline and how we operate it, I want to briefly go overview our overall architecture. So as you can see here, we actually divide our services roughly into 3 parts. The first part is what users use. We support over 1,000 different devices types: TVs, pads, iPhones, video consoles, or game consoles. And then all those devices, they have these Netflix apps, they send requests or they communicate with its edge services. Then the edge services will interact with our different internal services. We have this service-oriented architecture that consists of hundreds of different applications. They're not necessarily web services. Some of them are, some of them are not. They communicate with each other, they gather data from each other, and overall they present or they realize this integrated experience for the users. And also, these services generate a lot of data, and this data gets sent to different backend processors over this data pipeline, which we open sourced called Suro. So to put that into perspective, we're talking about 100 billion events per day, and at peak hours, we have about 3.2 million messages per second at peak time, or 3 gigabytes per second at, if we're talking about bytes. And the data gets dispatched into different processors like Hadoop clusters or Hive tables, or some of our Hadoop like applications running on top of Hadoops for batch processing. Or we also have this real-time processor and also real-time indexers like MetaMarkets, Druid, and Elasticsearch, and we aggregate data. We analyze them in real time, and then we present it into a dashboard or multiple dashboards depending on our usages. And what kind of events? We actually collect various different kinds of events. We collect the user interface events, for example, what kind of activities users are doing, like whether they search something, do they click a button, do they scroll a screen of movies, did they play a movie, things like that, and did they rate a movie. Also, we collect a lot of infrastructure events. If a request happens, we capture those events. If an RPC call is made, we capture such events. If there's an error being logged, we capture such events, so on and so forth. But then the key here is not really collecting data. Yes, we collect billions and billions of events per day, but the question is why? Right? What do we do about those events? If we only just collect them and then stash them somewhere, then we're just wasting money. What we really want is to make sense of those billions of events. What kind of insights we can draw out of those events. That's the end goal of all the activities or all the investment we make. And that's why we have this data pipeline. Most of them are open source softwares, and as you can see later, that you can also quickly assemble your own data pipeline or analytics backend with similar offerings. So on the very top, it's the Suro data pipeline. The first thing we need to do is to gather all the data, right? And then the heavy lifting is done by Suro. And also, we send data to the Hadoop cluster and use all kinds of applications or systems built on top of this ecosystem. And we also have our own internal tools to fill the gaps, which I'll talk about later. And also, we use Apache Kafka for longer persistence of log data, and for real-time processing, we also use Druid and Elasticsearch. Then here's what I'm going to do. I'm going to go over some stories. I tell you the stories of how we built this system. We didn't build this system in a day. We have very few people, but then it still takes us some time and multiple iterations to build a system. It's really like we how to devour a whale. Like we do that one bite at a time. And we started in a very humble way. We do this. We do log scraping. We capture logs, we SSH to an instance, and then we run, we perform some like script But over time, it's not enough, right? So we started using all kinds of ad hoc tools such as R or some other tools, Python, or people, as people like. And then we generate some kind of graphs or analysis to find the bottlenecks or to find out what's going on in the system. But they're all ad hoc. But soon, it's not enough anymore because something happens. The most important thing is our API usage growth, like the growth exploded. As a result, then the number of applications or number of services also proliferated. And so when we have so many applications and so much traffic, then we generate tons more data that a script just cannot deal with. But in the meantime, we still want to process data. So here's the first demand or first requirement. I'm sorry? Okay. First requirement from our teams. We want to process data in a batch mode as fast as we can. And so as most of the other companies do, we want to process data in Hadoop. And we want to write impressive scripts like this to process data and generate equally impressive visualizations of the data to find out what's going on. Right? Then because of this, we built our first version of our data pipeline. So from the left in the square are our application clusters. Imagine that you have hundreds and hundreds of them. They all generate all kinds of events. And in Netflix, we don't really restrict people from generating those events, right? Because we want to make sure that engineers can do their job as efficiently as possible. So that means they need to jump as fewer hoops as possible. So they can do whatever they like. They can just send a lot of events to somewhere, and they shouldn't be care about it, right? Because it's our team's job. Then we built this drawer in the middle. It's a single service. All the applications send events to this single service, and this service filters them and decides where to send those events to. And then initially, there's not many places to send events to. It's only one location, Hadoop cluster. And we use the EMR. It's called Elastic Map Reduce, offered by Amazon. So the data gets sent to S3, and S3 is already connected to the backend of EMR. So we can easily get data from S3 efficiently into Hadoop and then process the data. Of course, between S3 and then our Hadoop cluster, there's a demoxer. The demoxer takes all the generated sequence data files and then further aggregates them and process them and index them into Hive. Okay, so this is our first version of the data pipeline. Simple, robust, efficient, but doesn't have many functionalities. And also over time, we also developed a lot of different components in our on top of our Hadoop cluster. We have our own ETL tools, we have our own visualization tools, and we have our own web UIs. We also have different services to make our life easier. And we all open source them. HSFS, the Genie, the Lipstick, the Pigpen, and Semper. I'll briefly go over them one by one. So first of all, this is the foundation of all our services. It's Hadoop as a service. We have distributed teams. Each team needs to perform their own systems. Imagine that there's no service. It's just Hadoop. Then every team has to learn the ropes of how Hadoop works. And then, where do I go to look up my status? How do I submit my jobs? How do I track my jobs? What's going on if my job fails? There's a lot of things that we need to take care of. So that's why our data platform team builds this Genie, the Hadoop as a service, so that we can easily submit a job, we can easily track the status of what's going on, and then we don't even have to know where our Hadoop cluster sits. All we need to do is to go to a UI and then submit our jobs from there and track our status there with all kinds of facilities. And also, internally we use the Pig script a lot. For those who don't know Pig is from Yahoo Labs. It's like Google Seesaw. And we write scripts, and the scripts get compiled into MapReduce jobs running a Hadoop. But then the pig is still a scripting tool. Sometimes people want to figure out what kind of job is generated. How can I optimize it? Is there any way we can simplify our job scripting? This is where Lipstick comes in. It provides a visualization tool that we can just drag and drop to compose our jobs and then run it. And also, it shows the topology or the relationship between different jobs so that we can actually figure out where the bottleneck is or how we can reorganize the job or scripts to make the jobs run faster. And also in Netflix, we use multiple languages, and some people really love Clojure. So that's why we have this Pigpen, so that people can write native Clojure code, but internally it uses macros to convert this Clojure code into Pig scripts. That's why we say it's Pig married to Clojure. And Semper is really a library that provides additional layer of consistency checking on top of Amazon's S3 index through a consistent secondary index. We have different jobs and we have workflows, right? And jobs persist their data into S3. Unfortunately, S3 itself is not a strongly consistent system. It's eventually consistent. You write something into S3, you may have to wait for a while until you see the final writes. So in that case, but then the jobs cannot read stale data. That's why we built this system to make sure that different jobs will see consistent result even though the data is persisted on S3. And also this it's efficient ETL with Cassandra. We also persist data into, especially business data, into Cassandra database. Now, what if the data science team wants to combine the data, business data in Cassandra and also log data in Hadoop? Then there's got to be a way to extract data efficiently from the database without impacting our runtime performance of other services. This is where this piece of software comes in. It will directly go to the internal file format of Cassandra, which is this like append-only log files, and then run through, go over these files chunk by chunk to get data and then dump them into our Hadoop jobs. Okay. So that's just a very brief view of our offline analysis. And they make data scientists happy, and they do a lot of heavy liftings and generating a lot of useful data for us, especially used for business insights. But something is still missing. We still need something else, right? We make our business people happy, but what about developers? So this is where another iteration comes in. We need speed. But speed in what sense? So let's go over some of the operations like developers need to do. One is this. Let's say we are doing some post-mortem analysis, and we know something goes on. There's an outage about 3 days ago, or there's an outage, even there's an outage now. How do we know, how do I find out the culprit? How do we find out the root cause of the problem? Initially, we didn't have many tools. Well, we still persist all the data into S3 or into this HDFS of EMR. Then our team wrote this tool called HGraph, which is a glorified graphing tool that has most of the functionalities of a normal group and graph, except that it's running on the on the Hadoop cluster, so that it can scan a lot more files, a lot of files distributed on multiple machines than a single script. But still, it's a MapReduce job. It runs slowly and unpredictably. Then it doesn't really answer the question, what if I want to find out what's going on now? So we built a different tool like this. It's called Biopsis. What we do is we specify which cluster and which instances we're interested in. And then we're filling a bunch of query parameters, such as the files we want to search, the pattern we want to search in the file, and also a bunch of options like context, the time range, or maximum noise. It's just like a graph. It's still a graph, so keep that in mind. And then we run it. Then the tool will go to each machine and perform a search on the fly and stream back the data as soon as the first line of result becomes available, so that we can see what's going on and we can see the context of theirs. And also we visualize on the fly based on the data. Of course, this is only available for access log because access log is more structured. For like ordinary application logs, there's no visualization. But again, this is only for logs. Or what about our events? And also the visualization is very limited. We want something more sophisticated. So in summary, we want something that gives us more insight. We want to be able to aggregate data, index data, or inquiry data with different combination of dimensions in real time. Or we can say we want interactive exploration. This is especially important for DevOps. Okay. The reason is, oh, let me go through some. So let's go through some. Before we go through some use cases, I'll discuss why it's important for us to have interactive explorations. Because when something happens, usually that bad thing that happens is not familiar to us. Right? Because if something keeps happening, we probably have already handled it, and it will never happen again. So whenever there's an outage, whenever there's a system stress, it's something new most of the time. That means we don't know what's going on. So we have to explore. We have to try different queries. We have to imagine what ifs. What if this goes wrong? What if that goes wrong? What if we combine this condition and that condition and then figure out what's going on? So we have to issue a lot of ad hoc queries. And for those queries, we cannot pre-compute the combination of different fields, right? And also we cannot wait for long because an outage is happening at this moment. That's why we need real-time interactive exploration. So let's walk through some use cases. Here's one. Imagine on the very left in the blue box is client activity events. So we do collect a lot of user activities like user ratings or user interactions with the devices. And all the data are sent to Hive. But in the meantime, let's say I want to find out the geo-distribution or the distribution by zip codes of how many people started our movies. How do we do that? It's just a very small subset of all the user activity logs, right? In that case, what we really want to do is to filter the events. We want to say for all the client activity events with the name movie starts, forward it to a different location so that we can see their geo-distribution of such events as demonstrated by this UI. How do we do that? So in order to do that, we need to solve these challenges. One is for the app owners. The app owners really don't care. By app owners, I mean those people who code the applications. Remember, we have multiple services. Each team owns a lot of services. So app owners are the people who write those services. They don't really care that much about events. They just want to send or forget. They have a lot of, their job is to build functionalities into their services. And the messages are really requested by data science team or by DevOps team. It's not that important to them. But then for data scientists, the data becomes more interesting and they have more sophisticated needs. They do run validations, they need to perform ETL processes, they need to perform batch processing. And for DevOps, they probably need to perform stream processing. They need to run the ad hoc targeted interactive searches on the data. Right? How do we merge these two requirements? How do we satisfy three different groups of people, even though we want to pick and choose events and then process them on the fly? Right, the first thing is, then the first answer is we want to do message routing. Right, again, we have the previous picture. We have this the same events. They are all sent to Hive. In the meantime, we want to pick some data and then we want to send it to a different processing unit. That's why we have this routing component. We can use some path description language to find out only the events we're interested in and then forwarded them into a different location. And the key here is this routing is dynamic. And this routing happens on the fly upon the change of configuration. And here's one example. We built this demo about a year and a half ago to show the real-time effects. What you see here happens, well, it's a capture demo, but really there's no editing whatsoever. We have this user activity window, user activity events in a time window. We say, hey, show me the geo distribution of the users who played the House of Cards in the last an hour or in the past 10 minutes, and show me the results now. And this is what we saw. So in summary, we want to consume data selectively in different ways, and we use these routing components to do that. And the routing component is already integrated or is part of the Suro pipeline. Okay. And also, so now we have routing components. We route it, but where? Right? We still have multiple consumers or potentially multiple processors. That's why we put Apache Kafka in there. The events are being sent to Apache Kafka and first. But why do we use Apache Kafka? Well, the reason is Apache Kafka really suits our needs. Apache Kafka is a message broker, so it supports multiple consumers. Different consumers can consume messages or consume log events at their own paces. And also it's high throughput. Potentially we may send a lot of data over the pipeline. It could be hundreds of thousands of records per second or even millions. And also the data is persisted and replicated. So it gives us added durability. But there's more. We are sending data, then the key is to process data. So we have to have more stuff in there. But what kind of stuff? So here's one more use case. Intelligent alerts. Imagine you're a developer. You man your own services. You create a lot of metrics or a lot of events. Right? And you really don't have time to look at those events all day, right? You have your busy life. You have to code a lot of new features. You have to fix your bugs. But when something happens, especially if a bad thing happens, let's say if there's a surge of errors, you want to be notified immediately. But that's just part of the story. When you're being notified, you still want to figure out why, right? Without proper tool, then it's really ad hoc. You jump around, you look at the dozens of different metrics, you try to find out what's going on, and then you go to your logs, you go to a place to search your logs and try to correlate these logs. So over time, you build your experiences. But still, it's time consuming and it doesn't work all the time. And what we really want is, we want to find a context. We want to say, hey, here's the alert. But given the context of this alert, here are a bunch of hints you can use. And this is what these intelligent alerts provide. When there's a surge of error, then the owner of the application automatically gets these alerts with this graph to show there's a surge. But on the top, there's also a link to our real-time indexing service. The link says top 10 errors grouped by application, login class, hostname, and line number. So essentially, it allows us to find out all the distribution of the errors based grouped by application and the location of this of the errors. So we click on that link, then this is what we get. So you can see all the all different kinds of errors grouped by applications, host names, and locations. The goal is to find out outliers. Right? At any time, the system may have a lot of different errors, but usually there's one error that's prominent that you want to look into first. Unfortunately, in this case, we don't really see outliers. Yeah, there are about 4 errors. They have slightly higher numbers than the others, but nothing is prominent. Then what do? Well, because we have this really powerful UI, then we can just get rid of one dimension. Instead of grouping the errors by application hostname and locations, we can just change our query on the fly to group them by only application and locations. So we want to see the cluster-wide distribution of errors. So let's do that. We remove one dimension. We click submit query. Then you can see the result comes back in seconds or even sub-seconds. And now we can see there is a very distinctive error, the top one, right? It has a much higher number than all the others. And it has something to do with the application merge web. So at this moment, we know where to look at. But what about the details? This is the aggregated view, right? We want to see the details. So what we do is we can click on the any text in that table associated with this error. So this is the distribution. We click on the link. Then we jump to the raw data of all the errors. Now we can have an expanded view and we can see what's going on. And it really says it's the error retrieving kids genre from our services. And this is a detailed, and we also know the location, including the line number and the class name and method name of where that function happens. So it becomes much easier to developer to figure out what's going on and then apply a fix. Okay. So to summarize, this is what we need. We need to run the ad hoc queries with different dimensions, and we want to run them on demand. And also we want to have quick aggregations, especially top-end queries grouped by these given dimensions. And we also want to see time series. We want to see time series because we want to see trend, because we want to compare trends. And also we want to have quick access to raw data using Boolean queries. This is where the search engine really comes in. And by Boolean queries is you want to say, hey, I want to find out the errors of application ABC, but not application, but not cluster DEF, right? So you want to have this kind of logic combinations. Okay. Then let me introduce Druid. Druid plays a really important role in this whole real-time indexing and aggregation service. It provides this rapid exploration of high-dimensional data. We have a lot of dimensions associated with our events, but then we can group our events based on different criteria. We can filter them. We can apply different groupings on the fly, and also it provides the fast ingestion and querying. Druid makes the ingest. Once the data is ingested, then the data becomes almost immediately available on Druid, and it becomes available for querying too. And also it provides time series, and time series supports the same dimensional grouping and the same filterings. So it's very flexible and fast. And also Elasticsearch. So Elasticsearch provides us with this capability of real-time indexing. And also it has this killer feature, Boolean search. Of course, it's a search engine. So search engine supports Boolean searches. And also it has this great UI called Kibana. The use case I just showed you has this UI. It is using this Kibana UI. We just modified it a little bit. Okay, so here's the reminder of the old pipeline. We have applications. We send data to Suro forwards data into S3, which gets picked up by our demuxing service, and then the data gets persisted into Hadoop. Now, here's the new real-time part. Same events, but with different filters, then it gets dispatched into 2 more processing units after we send data into Apache Kafka. Okay, here is a more elaborated view. So on the very left, you can see we have events. We color them to indicate that they might be different events with different data. And then we can just perform this routing rule to filter the events. And you can see the red events get sent to Kafka and the blue events get sent to S3. But there's really more. Right? So it's not really all about counters and time series in the metrics. Sometimes it's about something more sophisticated. Here's the picture of our internal services. can you really see what's going on? Can you really see their dependencies? Well, it's hard for me. It's very ad hoc. There are a lot of paths. How do I know how many services do I have? How many know which dependencies, especially transitive dependencies, do you have? In case there's an emergency or an outage, how do I know which link is the hot link that I should look into? That's hard. Right? But then we're collecting a lot of stats or a lot of events. One of them is this request events. Whenever a service gets a request, the service will record something like this. Whenever a service sends out a request, it will also record the request log like this. But just by looking at this log, can you see anything interesting? It's hard for me to see. And also, we're not talking about only 4 rows. We're talking about, well, this is request traces. So we're talking about billions and billions of rows per day or millions per second. In that case, it's really hard for us to gain any insights from this data. But if you look at the fields, we have request ID, we have parent ID, we have a node ID, which is like child ID, we have service name, and we have stats. So we're talking about relationship, right? Parent, child, it's like graph. So this is what we get. So let's say we enter a name called application name, and then we click draw. So within seconds, this is not live demo, by the way, but this is real from production data. I just obscured all the service name. So you can see from within seconds, giving a service name, we can ask what are all the dependencies, including transitive dependencies, this given service has, and then immediately we can see this. And this data, this graphical data, is really from the tabular data you saw in the previous page. But there's more. This is just dependencies. Because we capture our data, all the edge has rich information. So we can click on this edge. Did I click on that? Yeah, so by click on the edge, then we can see more information. We can see the call volumes between any 2 services. We can see the distribution of HTTP responses. By the way, there's more than HTTP response. If the services are not web services, then we see different response code. But it's just because the link that in the demo I clicked happens to be HTTP or web services. That's why you see the response code from HTTP. And again, we can click on those distribution to see the details. Kibana UI again. And then these are the real data, similar to that table I showed you. That table is a simplified version, and this is complete version. Okay, so we call it distributed tracing. Okay, so I think I've shown enough different use cases and systems to justify the needs of data pipeline and also the batch processing, also the real-time processing. We really have a system that supports all this, or we can say a data pipeline to glue all the components together, which is the Suro, and its different used open source components. And also, let me talk about a few design decisions we make and how we build the system. And they're just general principles used in the system designs, but they're worth mentioning. So the first thing is we will really want to make it simple. Right? Simple in every way. So first of all, we want to make message producing simple. As we said, the app owners or the owners of the application that produce messages do not want to deal with event producing all day. They really want to send a message out and forget about it. So we make a simple and uniform API. It's called publish. I don't know how simpler can that be. Whenever the user construct the event, they just call message bus.publish, and then the events get sent out. It is the client that handles the buffering, the concurrency, the synchronization, the retries, the fault, the error handling, or the load balancing. It's all hidden from the user. And the consumption side is also simple with certain level of flexibility. The consumer side follows this streaming and the asynchronous program model. Whenever we call observe, then we get a stream of events back, and then we can acknowledge that that the event is consumed. Of course, it can be automatically acknowledged as well. And also, we can pause the stream if we want to temporarily stop consuming messages, and we can resume that. So really, from the consumer point of view, all they know is they get back a stream of events, and then they can register callbacks to handle those streams or of events whenever there's a new event comes. And this is implemented using RxJava, which is also open source by Netflix. RxJava follows this so-called functional reactive programming model. It treats this data as a stream and then you can register functions as callbacks. And also, it provides all kinds of powerful streaming APIs. You can easily transfer your streams, and also it hides all the intricacies of concurrent programming for you, so that you can focus your attention to the logic streaming processing without worrying about concurrencies. And also, it separates the logic from threading model. You can test your code as if it's running in a single-threaded application, and then later you can introduce schedulers to make it parallel or concurrent. And here's a bunch of design decisions that almost every data pipeline makers will make. The first thing is we care about application stability and throughput a lot. It's our top priority. We have this in-process clients, right? Like it's JVM based. We have to collect and send out events along with the application. So we don't really want to make the application run slower. We don't want to make the application unstable just because we want to send out some events. So naturally, all the operations by default is asynchronous. And also, we do aggressive buffering. We make sure that the messages are buffered before we can send it out. Buffering really is the very effective way of increasing the throughput of streaming. And also, we drop messages if necessary. Let's say if the application slows down, or if there's a temporary network glitch, then our internal buffer gets filled and no message gets sent out. In that case, we don't want to buffer our messages unboundedly. We want to make sure we have enough memory for application to continue functioning. That's why we drop messages. Sometimes it sounds controversial because we're losing messages, right? But then the counter argument is it's rare that we run out of space, and it's rare that we have network glitches or application outages. And also, we're not talking about single messages. We're not tracking whether a user has submitted a purchasing order. We're talking about getting insights out of millions and millions of messages. And here, really, we're performing statistical analysis. And the law of large numbers really kicks in, right? Even if we drop a few messages, our analysis should be robust enough to compensate that. And that's exactly what we're doing. That's why we can afford losing messages occasionally. Besides, by losing messages, we're talking about 0.001 or even less % of message losses. And also, anything can fail, so we have to keep that in mind and then build our system around this. And also, in order to make sure that our system is truly resilient to errors, we actually have this Chaos Monkey. So Chaos Monkey is the service that randomly picks a service or a healthy server from different clusters and just killed it. We kill about 1 instance per day, and we make sure that the system runs as usual without losing messages and without impacting its functionalities. So here are the fault tolerance features. Well, the first one is we do the write and forward as usual. The difference is we write messages into a elastic block storage first before forwarding that to the next location. Elastic block storage also short for EBS. EBS is provided by Amazon. It's Amazon's solution of network attached hard drive. So we write it to EBS, and the good thing about that is, let's say we write a bunch of data into EBS, and all of a sudden the application crashes for no reason. Now we get data on a disk, and if in normal situation we lose data, right? But in EBS it's persistent. So once the application crashes, then a manager will detect that a EBS volume becomes alone or becomes detached. Then we have a manager that will automatically reattach this EBS volume to a different service, and that service will start draining this EBS before it starts taking new incoming stream of messages. So by that, we guarantee that no data or little data will be lost. And also we have this disk-backed queues optionally. It's also using an open source package called BigQ that you can find on GitHub. So the disk-backed queue provides the same interface as the array blocking queue. We wrap around it so that user just queue their messages. It's as if they're queuing the message in the memory, but really they are queuing the messages into disk. By doing this, we get a much larger queue when outage happens. Let's say we have some really important data that we can afford storing them in the disk for a few hours, and we just don't want to lose them. Then by using BigQ, even if our outage lasts for hours, we still have all the data on the disk, and then later we can drain them without losing them. And also we have customized scaling down. And the background is all our services are auto-scalable. Right, when the traffic is high, then we add more instances. When the traffic volume is low, we reduce the number of instances from a cluster. By reducing the number of instances, we really need to kill those instances. But then if we kill a pseudo server, then it's possible we lose data, right? Because the pseudo will have internal buffers everywhere. Then what we do is we implement this customized cooperative scaling down. Whenever we want to kill an instance, we send a signal to that instance, notify the instance that it will be killed. Then the instance will say, oh, I'm going to be killed, so I'm going to stop taking traffic, and I'm going to drain my buffers. So once it drains the buffer, it will change a flag to indicate that it's ready to be killed. And then a service will come along to kill that instance. So with this feature, then none of the instances will be suddenly killed. They will always get a notification so that they have a chance to drain their internal buffers without losing any data. Okay, so with all those features, with all these designs, we have this complete picture of our data pipeline. We have application cluster sends billions of events to the pseudo cluster, and then the pseudo will just dispatch events based on user-defined criteria, and also these criteria can be changed on the fly during runtime without restarting server. And then we can install different consumers behind either Apache Kafka or MapReduce like cluster called EMR to process this data. And those are just 3 examples. We also have more different like other real-time processing units that we don't have time to talk about today. And I guess there's more to do. So I really encourage you to look at all the offerings on the Netflix OSS, and you're always welcome to join us or contribute more into our open source offerings. In the end, we build our systems on top of this, on top of all the open source softwares, and I'm sure if everyone contributes to the community, then we can make this community even stronger, even better. And that's it. So I guess I'm open for questions.
Danny, thank you so much. That was a great presentation, and thank you for walking us through it. And I have a bunch of questions that have come in through the GoToWebinar console. So
Thanks.
One of the questions is addressed to you, obviously, is what was the reason why you chose Druid over, for example, a tool like Graphite or something else for the visualization?
So choosing Druid, so before we choose Druid, we actually look through a bunch of a bunch of different choices. For example, we look into using Cassandra, but then the problem with Cassandra is it doesn't really support Boolean search or grouping by different dimensions. We look into a relational database, but then the scanning of a relational database is too slow. We look into pre-computing. Oh, excuse me. We look into pre-computing of different dimensions first, but then pre-computation, it's a exponential problem because we're essentially talking about generating all the combinations, giving a set. It's a power set. So the complexity, the space complexity is 2 to the power of n. N is the size of the set. So when we look at all these different offerings, none of them is fast enough or can handle large enough set for us. And Druid can do this job for us. That's why we choose Druid. As for the monitoring tools, so what we are doing here is especially that intelligent alerts and the Druid query or Elastic query, they're for events. Right? So we're trying to draw as much information out of our events, not metrics. So for metrics, we have our own monitoring tool. It's called Alice. It's based on RD as well, but then we didn't really use Graphite. We have our internal tools, but then it's I don't know why they chose that tool though.
Okay, great. That's a great answer. I have another question from one of the webinar attendees, and the question is, does Shuro work in a private cloud environment, or is it only designed for AWS?
It will work with a private cloud. So the open source version doesn't assume that we have an AWS. It just assumes that you have it running. Actually, it doesn't have that. No, it doesn't have that assumption at all. So you can run it anywhere. You can deploy that into your internal servers, or you can deploy that into different systems as well. Oh yeah, I was going to say is we only tested on a Linux platform. But in its Java code, we didn't have any native bindings. So supposedly you will be able to run on different systems.
Okay, great. Another question I have is, obviously to build a logging and monitoring solution like this, it takes a lot of time and effort. Mm-hmm. So the question is, how long did it take you guys to build Netflix Shuro at a level where it is, the current level of maturity?
That's interesting. It doesn't. Okay, so I would say it takes. I don't have accurate number, but let me tell you a slightly longer story. So initially, Shuro is based on an Apache open source software called Chakwa. Right. So we have something to work on, and it was only one person working on that for about less than a year to have everything stabilized, to have all the added monitorings and all the integration with an Amazon cloud. So it's an internal version. And later, the owner of Chakwa left the company, and then 2 people took over, me and Jay. And it's just really 2 of us. So we built everything. For all the things that's working, it's just a few months. And that's only because we are assembling pretty powerful solutions together. We didn't write Kafka. It takes a really good team, years of work to make it happen like this. And then we didn't write Druid. We didn't write Elasticsearch. We really just put them together and then build all the glues to make them function. So it didn't take long. Okay. I guess that's one of the points I have in this in this talk. If you use the right component, then you can do something similar in a very short time.
Okay, great. I have another question around the business. So the question is, what is the business impact that you were able to generate using Netflix Shuro? For example, are you able to speak to specific benefits or examples or stories where problems were fixed faster, or reliability was increased, or what are some of the business outcomes that you're proud of that you think Netflix Shuro helped at Netflix?
Well, there are 2 folds. one is without this rule, then the business people won't be able to get their data to analyze. So I say it's a central piece in the whole infrastructure of Netflix. We have only one single data pipeline. All the data is sent to this data pipeline and then gets dispatched in different places. So all our the machine learning clusters, the business reports, the predictions, they all get data from like behind the zero. So that's on the business side. Well, on the operational sides, it provides because the data intelligent alerts is generated on every 10 minutes. So, and then also if something happens, then we can get this one, well, on average it's every 10 minutes. Sometimes it's faster. So actually we had some like internal mini outages, and then this alert can alert us before other alerts kicked in. So we actually get to respond to it much quicker than before. And also that this distributed tracing is really important for us, because now we can see the real relationship, the dynamic relationship behind that's happening at this moment, and we didn't have that functionality before.
Great. Thank you so much for your time, Danny, and I want to be respectful of everybody else's time, and it is exactly 2 p.m. Eastern. Danny, I really want to thank you for participating in this
my
webinar.
pleasure.
And giving us this wonderful overview. And for the folks that are in the audience, thank you very much for participating. Definitely go in and sign up on CloudDC Meetup. The URL again is www.meetup.com/CloudDC. And do provide us your comments and feedback. And if you like this session, we'd love to do more of these. And we have wonderful speakers like Danny, and because of the webinar technology, we are able to pull them in from the West Coast, where a lot of interesting innovation obviously is occurring, and bring sort of a rich set of topics to you. And also do let us know any topics that you might suggest. So with that, we are trying to get permission to go in and record the session, and we'll try and make the slides and the recordings of the webinar available on our site. So give us some logistical space to go in and make that happen. And again, thank you very much for participating. And Danny, thank you again so much.
Thanks, everyone. And thanks, Gaurav, for organizing this.
Yep. Bye-bye.
Bye.